You guys did not have much homework, so I don't want to spend too much time going through it. We got question 1 here that says, which graph represents the relationship between the angle of insolation and the intensity of insolation? I'm seeing some right answers. How about the rest of you? I just want to check what you say for an answer. Okay, like this means everybody. What do you pick for an answer for number 1? Okay. So first thing I want to ask is, do you know what intensity means?
Yeah.
If something's really intense. Okay, very hard, very strong. Okay, so like if like I'm being intense, I'm a little extra, a little strong, a little crazy. You're right. So I want to make sure you know that. So we want to know which one, the angle affects how strong the sunlight is. And what I want you to do is picture what we did with our flashlights the other day. When you had your flashlight at a low angle, which means your flashlight was shining down, not like this, but like that on the paper. So when the sun is low in the sky, is the sun strong or weak? When it's low in the sky, it's weak. So here's an angle that says low. So we want weak, so not strong. So not number 1. Number 2 does have a weak intensity at a low angle, so that's still a possibility. But number 3 as well. But this one says low angle, strong intensity. So then we got to look here. A 90-degree angle, are we going to have a strong sun or a weak sun? Strong. So here's 90. This one says 90 would have a weak intensity. So that's not it.
That's definitely not.
We've got answer number 3. Low angle, weak sunlight, 90 degrees, strong sunlight. All right, this one says again, make sure you always read the reading. We've got the graph shows air temperature on the clear summer days, 7 a.m. to noon, 2 different locations, Florida and New York State. So we look at the graph. We've got time of day. We've got temperature. We have a line for New York and a line for Florida. So we see that New York is a little colder no matter what. And Florida gets hotter faster than New York does. And so it says air temperature rose slightly faster in Florida than in New York State because Florida has, can I see your answers again, please? Florida has, yes, I'm seeing all the right answers, has a higher angle of insolation. What does that mean? They have a higher angle of insolation. The sun is higher. Hey, so not Zach, not Jeff. How about the rest of you? Why is the sun higher in the sky in Florida? Closer to the equator. You were good. I do want to point out answers 3 and 4. Why do you think they put answers 3 and 4? To mess with your head. Because Florida's closer to the equator. Florida's not any closer to the prime meridian than us. Plus, does the prime meridian have anything to do with how strong the sun is? Nuh-uh. So don't fall for their trick. Number 3, the average temperature of the North Pole is colder than the average temperature of the equator because the equator, what does the equator do that makes them have higher temperature? Which one? All of you, put your fingers up. Yes, I'm seeing mostly right answers. The equator receives more intense insolation. I saw some number 1s, less ultraviolet radiation. So first of all, ultraviolet is not what makes us hot. That's the infrared rays. And second of all, they asked because the equator, they would receive more ultraviolet anyway. So that can't be the answer. All right. Any questions on those 3? All right, so we're gonna switch on over. We already did page 14 completely, correct? And we did the very top of page 15?
Yeah.
Okay, now we're talking about heating up land and water. And before we talk about that, I need to take you on a little imagination field trip. No, imagination. No, an imagination field trip.
Oh, outside.
Yeah, no, I think you guys forgot what the word imagination is.
Zach has a very strong.
Does he really? He imagines that he is a good singer.
Oh, that's not imagining.
Oh,
Yeah,
I
it's
beg to
facts.
differ. Sorry, I wasn't. I forgot to get this ready. So give me 1 second.
Imagine Dragons? What's Imagine Dragons, already? Never heard of it.
Believer.
What?
Isn't that Imagine
What?
Dragons?
Yeah, you got it. I want you to tell me what Imagine Dragons is, huh? Here.
Okay.
No, that was Imagine Dragons.
No, it wasn't. Why does this do this? All right. Hey, here is your field trip we are taking on our imagination.
Wait, I could be there right now. Is that Florida?
I don't know, it's wherever your imagination takes you. So it could even be your very own backyard, I guess. But I had to actually get the picture up there because I'm having a hard time imagining that after looking out the window.
Is that your house?
No. No pool for me. So here is your field trip you're going on in your imagination. I need you to picture it being like August.
August, that looks more like.
August and where? Yeah, that does look like July.
That looks like July. What's the difference between August and July?
I'm thinking
More sun.
More, okay, we don't need to even get into that. That's
We
besides
should
the
have
point.
put pool in August.
Picture a very hot freaking summer day, whatever month you want it to be.
21st.
It's still not getting it. Anyway, you're there. You go out. You're ready to hang out here. You're sitting there. What gets hotter faster? The pool deck or the water?
The pool
Water
deck.
deck.
Okay, you guys know that?
Yeah.
You all experienced that.
Yeah.
All right, perfect. So you've already experienced something.
Hopefully the water isn't that warm.
Okay, right. Hopefully the water is not that warm. Okay, now I need you to picture that same day, around 9:30 at night.
Ooh.
The water.
Ooh, wait. Beautiful, beautiful night swimming. There's like night
I love
swimming.
night swimming.
No,
I love night
No,
swimming.
it's bigger than mine. Yeah, because we have a bunch of wood, so I always think that poop.
I'm thinking of it, yeah. Night swimming in this pool. What cools down faster, the deck or the pool?
Yeah.
The deck cools down faster. So guys, why does the deck heat up faster and cool down faster?
Because it's a flat surface.
Because
We got flat surface, darker. What do you think? Good.
because it's not water.
Because it's not water. Yeah, I mean, I think that's probably close to the right answer. I mean, I can't say it any better myself. What I'd like you guys to do is grab your reference table.
We have to.
Yes, grab your reference table. I'm gonna put it on the board so I don't forget next period. Front reference page, front page, upper, what is that? That's the right-hand side.
Alrighty.
Front right, it's called the specific heat chart. Take a look at some of that information in the specific heat chart. So upper right-hand corner, it says specific heat of common materials. I have it on I'll pull it up here too. So here's that specific heat chart. So we got some materials. You'll notice water's on that list. Now wood or concrete's not on that, but there is some things that we can kind of relate to. So how about granite and basalt? What are those? Those are rocks. And then you've got iron, copper, and lead as well. What are those?
Metal.
Metals. So how about if we, instead of having the pool deck made out of wood like it was in that picture, What if the pool deck was made out of copper? Okay, so the same is still true, right? Which one heats up faster? The water or the pool deck made out of copper? Copper. So you still get that concept. So how do you think we can go through this chart here to explain why the water takes more, or why the water takes longer to heat up? What do you think this chart is trying to tell you? Okay, it is first on the list.
How big?
So what if I help you by saying joules is the unit of measurement for energy? Just like feet is a unit of measurement for length, joules is a unit of measurement for energy. You wanna give it a whirl, Jeff?
Because water has more shelf,
Has more what? Joules, okay. Okay, so it has something to do with the fact that water has more joules. Let's break apart that last column there. That specific heat says joules per gram degrees Celsius. What that means is how much energy is required to heat up 1 gram of substance 1 degree Celsius. So if we look at that last column, how much energy does liquid water require? How much energy does it say?
4.8.
Yeah, 4.8. How much would the copper take?
30.38.
0.38, so a lot less energy. So if we keep that in mind, why does the pool deck heat up faster? Because it requires less energy to heat up iron, copper, or lead. And that's what we're going to put right there on the land versus water bullet. These are the only 2 bullets. I know they're a little longer than you're used to writing in that spot, or writing usually, but that's all that's going in all those lines. I'll let you write and I'll shut up. Mhm. So my example, I hope you understand that I was using the pool deck as an example of land, and then the pool water, obviously as water. You did, okay, good, I'm glad I explained it. Okay, so we can both play this game, Sarah.
Okay, good.
So the land always heats up faster because it has a lower specific heat. Or in this case, I worded it the other way, but it means the same thing. Land heats up faster than water because water has a higher specific heat. So clearly, we got to make sure you understand exactly what specific heat is before we continue to talk about this too much. That's the next bullet, is just the definition of specific heat. So the next bullet says specific heat is the amount of heat, again, that's measured in joules, needed to raise the temperature of 1 gram of substance 1 degree. So to be honest, those numbers on that reference table, we don't really even need to understand like what exactly 4.18 joules per gram degree Celsius means. We just need to see that it requires a lot more energy to heat up a gram of water 1 degree than it requires to heat up a piece of lead. And from your common sense, you guys already knew that. It takes a lot more to heat up water than it would to heat up a metal pan. Just in case we get lost on ESRT page 1. Oh, we're not moving now. There we go. Sorry, get out of the way. I don't know why that's not getting out of the way. It says the higher the specific heat, the more heat energy required to raise the temperature. That's the last part there. It says ESRT page 1. The higher the specific heat, the more heat energy required to raise the temperature of the material. So this is stuff we just did 5 seconds ago and you already figured it out. So just giving you the notes to go with it. Maybe a little longer, 5.
Yeah, just a minute.
Okay, sorry. We are gonna have 5 questions. All right, so on your reference table. Again, you guys were able to tell me this without too much thinking already. So I'm not sure how much work we need to do on this. Again, which one of these heats up fastest?
Lead.
Lead. What I think I would do is add that label. Fast. And slow at the top.
Ease job.
If you got those labels, I'm pretty sure you'll be able to see that. So liquid water heats up slow because it requires 4.18 joules of energy to heat it up 1 degree. Where lead only requires 0.13 joules of energy. Now, if you ever forget, well, which one's fast and which one's slow? I want you to imagine this little experiment. And I specifically said imagine because I don't want anybody to do this for real. Can you guys picture making a pot of macaroni and cheese? Now here's the part of the experiment I don't want you to do, but I know you can do it in your brain. You have the pot of macaroni and cheese with cold water and you're about to put it on the stove. You put it on the stove, you turn it on. Put your hand, one hand in the water, the other hand on the metal of the pan. We got one hand in the water, one hand on the pan. Which one can you leave there longer?
Pan in the water.
The one in the water, you're just messing with me, right, mister?
That's the water.
Okay, yeah, you can leave it in the water longer because the water heats up slow. So if you ever have a reference table that doesn't have labels, which you will on your reagent,
Picture the mac and cheese.
you can picture the mac and cheese and label it real quick. But it sounds like a lot of you guys knew that already because I said you knew the whole pool deck scenario. And then if I switch the pool deck to metal, you already all knew that heats up faster than the water. So I think you guys get this concept. So let's test your concept. You have these exact questions right there at the bottom of page 15. Try A, B, and let's do A, B, and C together. Which material on the specific heat chart heats up the fastest?
Lead.
Lead. I mean, I'm not sure if I put that. Nope, didn't put it there. So yeah, lead.
Thank you.
Which material on the specific heat
Water.
chart heats up the slowest?
Water.
Water. Oh, guys, did I forget to point out, did you notice that it says liquid water, solid water, and then water vapor? And did you also notice they have different numbers for each one?
Yeah.
So just be very careful. You should probably label that liquid water. And then question C is similar, but makes you think a little bit. Which one needs the most amount of energy to raise its temperature? Again, liquid water. Yeah, liquid water.
I didn't do it.
You didn't do anything. Liquid water takes the most amount of energy to raise its temperature, just because it's at the top of the chart. It's got the biggest number. Now, D is just a little bit different. In each step below, circle the material that would heat up the fastest. So I already did the first one for you. Water, iron, and copper. Why does copper heat up faster? Because it takes less energy. It's odd. So copper, my choices again were copper, iron, and liquid water. Copper heats up the fastest because it's low, it has a lower specific heat, takes less energy to heat it up. I'm gonna let you guys finish the remaining 5 of those circling jobs on your own. You're going across ice, basalt, or granite. Circle which one heats up the fastest. You're all done. Give everybody else a chance to be all done too, please.
One.
Rough, Sarah. All right, what do you think, guys? Which one heats up faster? Ice, basalt, or granite? Granite? I guess I should grab my reference table, make sure you're right. Yep, granite is the lowest one. How about lead, water, or iron? Yeah, lead's the lowest. Have any of you ever had lead you've melted?
No.
But
Lead is a metal.
I don't know.
It'd be- Well, we don't have pencil lead anymore. Some people will do this when they're making like sinkers for fishing. You could have those. Never mind, let's keep going.
anyone that has lead and loves the answer.
Lead.
Okay, again, lead. How about iron, basalt, or water vapor? Iron,
Copper.
copper. By the way, dry air was on there. I don't think I just want to make sure you know what that means. It's air with no water in it. Dry air. I know, mind blowing, right? All right, last one. This is like the moral of the whole story here. Why did we do this lesson? Compare the heating and cooling rates of land and water using the term specific heat to explain your comparison. So we got to compare how fast water and land heat up and cool down using the term specific heat. How should we start this sentence? No, I don't think so. We can let you
The
go.
rate of. Wait.
We're just comparing land versus water. So let's start off the bat. Which one heats up faster?
Well, land.
Land. That's the start of our sentence. Land heats up faster than water. Does that answer the question yet?
No.
No. You want to finish it, Jeff?
Land heats up faster than water due to the specific heat in water.
Yep. Due to the specific heat being lower. You could word that slightly different. That gets the point across. I probably would have kept it a little more simple and basic. I would have said land heats up faster than water because land has a lower specific heat.
That's the same thing.
Yeah, it has the same thing.
Same thing.
Jeff uses fancier wording than I do.
I like Jeff.
Not gonna lie, I don't use fancy words.
I think Jeff is better.
Yeah, the do too. Do too to me sounds like fancy words. I like the fun. Actually, I prefer just cuz.
Yeah, but that's not a complete sentence.
Yeah, I know, but I'm not a
You'll fail
complete
your
sentence
English
kind of person.
Wrong.
We passed it a long time ago before there was even an 11th grade English reader. So good news, I'm done. All right. One more thing, we got about 15 minutes. So for the record, guys, your homework is page 16. There are, oh wait, we're not quite even done yet. So at the top of page 16.
Oh, no, not that.
Yep, at the top of page 16 is one of those fancy sentences again. And maybe I'm in the wrong here because I think it's fancy and maybe Jeff thinks it's just normal English. But the sentence the Regents love is on the top of the page there. And it says, a good absorber of electromagnetic energy is a good radiator of electromagnetic energy. We need to translate that into words.
Oh, I know.
So what does it mean, a good absorber of electromagnetic energy?
Whoever is like, taking
So it takes in, and what the heck is electromagnetic energy?
the energy.
Yeah, it's this stuff down here, right? So it's all the energy the sun's shooting at us is electromagnetic energy. So if it's a good absorber of electromagnetic energy, in fact, which one, the land or the pool, is a good absorber of electromagnetic energy?
Land.
The land absorbs it really good, really quickly. Now what's radiator mean? Gives off, it gives off heat.
But you said it cools faster also, which means.
You guys got this.
So easy.
It is so easy. So what does that fancy sentence mean? A good absorber of electromagnetic energy is a good radiator of electromagnetic energy. It means if that material heats up quick, it cools down quickly too, like the land. Heats up quick, cools down quick. Unlike the water, heats up slow, cools down slow. So that's at the top of page 15. So it's great. 16, I mean. No, it's not quite over here.
You always do that. You make it seem like we're down in class and you.
Well, so, yeah, sorry about that.
We'll just be done. right?
No, we can't just be done. Got a little bit more to do, but as you're sitting here, label those 5 questions as your homework tonight. So questions 1 through 5 on page 16, right, 16? Homework, page 16, numbers 1 through 5. So again, just like last night, not giving you much homework, I would like you to actually put in the effort to do those 5 questions. But in the meantime, we're moving on to page 17, which is labeled terrestrial radiation. No, you know what? We don't have time to do that. I want to look at that teeny tiny little picture that's on page 16, and yours is much smaller than this, but this is what that picture looks like. I'm not sure if you can, anybody have any idea what this picture is?
The house.
It is a house.
It's a greenhouse.
It's specifically a greenhouse. Not a green
Oh.
color, but green like where you put plants in. These are supposed to be plants, but just out of curiosity, does anybody recognize what those are actually? Nope. Oh, you see it, don't you, Kate, or Kate?
Fossil.
Cat, you see it, don't you?
They look like fossil.
They're actually these fossils. They're letter I on the reference table. So I made this picture back when my computer skills were not all that great. So I just copied these because I thought they looked like flowers and put them there.
So weird.
I know, I'm a little weird. So this is a greenhouse. Does anybody know how greenhouses work?
Take the energy and then
Energy from where?
the sun and
Energy from the sun,
they put it on the flowers.
and they put it on the flowers. Good. Any more?
It like
It
traps.
It traps the energy from the sun. Well, how does it come? Yeah, it does. That's exactly what happened. But my question is, how can energy get into the greenhouse, but then why does it get trapped?
The windows are good.
Yeah, but why can it let heat and light in, but not out?
Turn off
Just,
the
it
windows.
absorbs it into it.
You want to try? Installation or installation?
And so,
It's not either, actually, but, so you meant like inflate, like the pink stuff? No, you meant installation, like incoming solar radiation?
greenhouses are literally plastic.
Okay, or like, they can be both. The key has to do with the bottom of page 14 here. What's going on the bottom of page 14?
Colors.
Okay, something about colors. Turn to the bottom of page 14, see if that might help. We want to know, how does page 14 help us explain why a greenhouse is hot? Who remembers when I said, guys, which one of those wavelengths or which one of these things on the electromagnetic spectrum do we get the most of from the sun? Or Kat, wait, hang on, it is visible light. Kat, do you have an explanation? It does have something to do with the wavelengths, you're right. It's not the color part though, but you've got the concept, Kat, you've got it. So Jeff says that visible light is the light we get, or what we get most from the sun. So visible light's here in the middle. How's a greenhouse feel, people?
Pretty good.
Why?
Like,
Cause it,
humid and muggy.
Humid.
and not just humid, but
Stuff.
hot. Hot and humid. Which one of these tells us about heat?
Infrared.
Infrared is the heat. So if visible light is what's coming in, it's got a little wavelength. And the glass or the plastic allows that little wavelength to get in. But it's the heat that's trying to escape. And it can't get out because heat has a slightly bigger wavelength. So that's why a greenhouse is hot, because the little waves can come in, but the big waves can't get trapped. Do you guys know how this applies to earth science at all? Has to do with our atmosphere.
Whoa.
Oh, you're seeing where I'm going with this, Jeff? This is called the greenhouse effect.
Oh.
Sound familiar?
That I
Oh, last 2 years ago, maybe. 8th grade, you learned it in,
last year.
you did?
Yeah.
What did you learn about, who's stealing my thunder?
Mr. Jeff.
Why the heck?
I don't know.
What did he talk about?
Climate change.
Oh. Well, I hope he didn't show my very favoriteest video about this.
We were just talking about.
Back in 2019, our team traveled to Nepal where they tried delicious wild sea berries.
You're gonna get blown away with the benefit.
Global warming, or none like it hot.
We actually did.
You're probably wondering why your ice cream went away. Well, Susie, the culprit isn't foreigners, it's global warming.
Global Wapoo?
Yeah. Meet Mr. Sunbeam. He comes all the way from the sun to visit Earth.
Hello, Earth. Just popping in to brighten your day. La 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 la. And now I'll be on my way.
Not so fast, Sunbeam. We're greenhouse gases. You ain't going nowhere.
Oh! Ah! Oh! Ah! Oh! Oh, God, it hurts!
Pretty soon, Earth is chock full of sunbeams. They're rotting corpses heating our atmosphere.
How do we get rid of the greenhouse gases?
Fortunately, our handsomest politicians came up with a cheap, last-minute way to combat global warming. Ever since 2063, we simply drop a giant ice cube into the ocean every now and then.
Just just like Daddy puts in his drink every morning. And then he gets mad.
Of course, since the greenhouse gases are still building up, it takes more and more ice each time. Thus, solving the problem once and for all.
But
Once and for all!
So I really think that video does a better job saving greenhouse effect than I can. And it's because of
Be on my way.
guys.
Not so fast, Sunbeam. We're greenhouse.
Not so
Popping
So
in to brighten your day.
where the sunbeams are coming to visit Earth, which part of what I was talking about does this represent? Where they just come to visit. Those are the small visible lights on the electromagnetic spectrum. They come, they visit, they try to leave. When do sunbeams leave Earth?
At night.
At night, when there's no sun out. So these sunbeams try to leave, but these
La 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 la. And now I'll be on my way.
fully.
Not so
This
fast,
is not something I've
Sunbeam.
mentioned.
We're greenhouse.
Oh, good. You know greenhouse gases. Do you know them?
Carbon monoxide.
Carbon dioxide,
3, 1,
Methane.
methane, and the other one's water vapor.
Oh.
Okay, so you guys know the basics of this. So we'll just take some notes on this tomorrow, but again, your homework is page 16.
We did this in like 6th grade.
Yes, you definitely have done this before, so hopefully this is
Where's
not.
the phone? The phone game? I'm not thinking about it. I'm being remote.
Oh, you are, you're that strong?
In 5th grade, we had to do a whole entire like
Like, I'm just gonna leave my friends.